Now I have to admit the weights and the weight of the classifier and the weight of the samples of the previous example has been made up. And let us have a look at how the Adaboost work in the samples in real terms. So let's open a notebook and have some cells. Because it is a stochastic algorithm as we introduced previously. We'd like to have a random generator that has a particular preset state, so that although the algorithm is stochastic, but we are able to repeat what we get. So for the programming and debugging purposes. And our X is NumPy and NumPy array. Let us arrange an array in this way. This function of NumPy gives you a series of numbers which resemble the range function of standard Python function, but arange can be used for float numbers instead of being limited to integers. Let's start from 0.1 and let the end point to be 1.01. It has to be slightly larger than 1.0 because the end point is exclusive and the start point is inclusive. So that's the rule. And the step size is 0.1. So check what we have. X, yes, just as what we have in the previous example. The target value for this X, let us make it as introduced. NumPy array. The first three target value are 1, and in the middle, remember we have a sandwich distributed the target values. In the middle 4, we have -1, and then we have +1 for the last 3 elements. Okay, let's check again. Correct. To initialize the weight, we will have 0.1, 0.1, 0.1, and repeat 10 times. Here I use a facility NumPy provides me called once-like, because look, we need to give a weight to each element in X. So it makes sense to have an array that has the same shape as X. Just in this array, instead we will discard the actual values of the element in X. We give 1 to each element in the weight array. So that is called once-like. Now we have an all-one array with a shape like that of X, and if we divide the elements in this array by the size of X, we will have the weight evenly distributed to each element of X. Let's also check the weight. Well, correct. So we're happy with the arrangement. Let's open a new cell, and in the next step, let us sample some subsets from the dataset. Note, we have multiple ways to draw random samples from a set. Let me show trap which is incorrect. Look, let us draw an X underscore equals random number generator, and there is a particular suitable function seemingly for this purpose that is called choice. If we have a look at the functionality of this one, it generates a random sample from a given array. Well, good. And the array should be X, of course. And well, that's the size to be the same as X original size. Makes sense. And oh well, that needs to be equal to. Replace means where you need to when you draw an element from the array, will it be allowed to draw again? As we introduced in this application for drawing subsamples for boosting algorithms, we actually need the random sampling to be replaceable. That means a sample could be drawn multiple times, so we leave this parameter to its default value of being true. And that is P is a probability according to which we draw the samples, which in this case need just corresponding to our sample width. Have a look. P, right? So let's write P equals D. This seems to be reasonable, and also we can do the same for Y. Let's just explicitly write a chain here. Makes the thing easier to understand. Okay, but look, this is a common mistake. If we do the sampling in this way, we would incur an error. Why? Because look, the random generator has been called once to randomly sample the samples from X and form the random subset of X underscore, and the random sample generator will be called again to randomly draw samples from Y and to form a random subset of Y underscore. But there is no necessarily correspondence to the random samples drawn for the X underscore and drawn for Y underscore, which is not what we want to train any algorithm. If let's have a look at the result if we do this operation. Look, if it is 0.6, the Y underscore value is 1. And actually, in the original dataset, the Y value for 0.6 should be 1, 2, 3, 4, 5th. 1, 2, 3, 4, 5th. Minus 1, right? So that is not the correct way. However, that is close to the correct way to do this. So instead of drawing random samples for both the X and the Y part of the random subset, we draw the samples by joining their index. To draw an index, we draw an integer from 0 to 9. 9 is inclusive. This function can accept an integer input as the first argument. This way it understands we need to draw an integer from 0, 1, 2, 3, 4 to 9. Okay, and the remaining part are the same. This part. In this way, we draw a set of random indexes, and then we form the random subset according to the random indexes and referring to the original dataset. Let's have a look. Well, this is probably correct. So for demonstration purposes, look, this step is unnecessary, but so to make the things looks better, we can do a sort. this is an implicit sort. After doing this, the index will be sorted ascendingly from the minimum value to the maximum one. So as the x underscore and the y underscore, which makes it easier to examine. Looks well, this time the random subset looks correct. I would like to rerun those cells because after have running the random sample generator multiple times, the generator has entered in an unknown state for us that is counter the purpose of have a certain preset of the state in the first place. Okay, run this one, and run this one. Well, look, now we have a set of random samples like this. The next step is to make a predictor according to the particular subset. In this case, it looks pretty clear where to cut. Here, look, when it is the value is in this side, the prediction are all -1, which of course, because this particular random subset does not include any value from 0.1 to 0.3. Well, it's a bad representative, but that is what we have. So at our best choice of a predictor at this stage is to have something cut the x value at this point from 0.7 to 0.8 and give the -1 to the left hand side and +1 to the right hand side. Let us create a predictor in this way. We manually created this predictor, so we see the training functions. Okay, we use something called lambda x. Okay, in Python, lambda means an unnamed function. This function is the simplest form that you can have to have some object that you can call and execute some instructions for you and return a value. This function, if we write it plainly, it is lambda x, and what I need to return, I will return 1 if x is greater or equal to 0.75. Otherwise, else I will return -1. After running this, we will have a function, and the function name is well, this function object is called a predictor1. Let's have a look what predictor1 will give us. .6. Let's print it. Predictor1 0.8. Pretty as expected. So we would like to use the predictor1, apply the predictor1 to all the values in the training dataset. So to do this, we can use another function called map. Okay, values in x and using predictor1. Have a look. Oh, sorry. Should in this order. This is what we have. Map is useful functionality by Python that is to let you easily apply a function to a set of values. So because each value of x can serve as the input to this predictor1, so we use the map, and the map will return us a list, and each element of the list is corresponding to an element in X, and the value of that output element would be the output of predictor 1 if we give the corresponding element in X to predictor 1. Okay, the prediction 1. Let us have a more explicit name, distinctive name. It's called output 1 to be nappy.s3 right. Is correct. That is to be nappy dot s3 output 1 equals y, and let us print. Also, we would like it to be a numerical value as type nappy.float. Okay, let's print this is correct. See what we would have. Good. That represents that this simple predictor 1 has correct predictions for the last 7 samples and wrong predictions for the first 3. Okay. Assessment on the element whether this predictor 1 is making a correct prediction. Now we'd like to calculate the weight for this predictor. So according to the equation, let's remember the equation should be look. I have made this cell to be a note cell, a markdown cell. In the markdown cell, if we put a pair of dollar symbol in between this, I can write mathematical equations, which is convenient. In this case, the equation is 0.5 with a logarithm, and in the logarithm there is a fraction that is 1 minus epsilon, and epsilon is the weighted error of the best predictor, and the denominator is the epsilon soft. So we have this equation as our reference. Now we have the is correct evaluation, and I think I should have a star here. So the epsilon star should be PS for this predictor. Let's call it EPS underscore 1. That should be 1 minus is correct because we have calculated the evaluation of whether the classification is correct instead of whether it is an error. So to get if it is an error, we use 1.0 minus. This is correct. Just flip the value between 0 and 1. This needs to be element-wisely multiplied by the weight, and our weight is none other than D. Okay, this is our weighted epsilon. Let's have a look what it is. Because now our this also need to be summed up, because now we have 10 equally weighted elements, and each of the elements has of course the weight of 0.1, and we have correctly predicted 7 of them and wrongly predicted 3 of them. So we expect this epsilon 1 is just 0.3. Let's look. Well, that is pretty as expected. And so the alpha 1 can be calculated accordingly. Alpha 1. That is, let us just copy the equation 0.5 times logarithm of 1 minus epsilon 1 divided by epsilon 1. Check. Yes. Now we have the weight for the first predictor. And in the next step, we need to evaluate we need to re-evaluate the weights of each training examples. To do this, let us also copy the sample weight update equation here. That equation is the sample t plus 1 of a particular training sample x, and then needs to be dt this particular x times epsilon exponential of minus or plus value of whether the symbol of this exponential number is whether or not this symbol has been correctly predicted, and the exponential number itself is just alpha. So let's look at the equation. This is not good. Okay, let us follow this equation. So this part, the dtx, we do not worry about because we already have it, and we need to calculate this exponential part. And in particular, because we already have this alpha t, so we need to give each element a plus or minus symbol. Okay. To have this symbol, we start from this is correct evaluation. If it is correct, we need to give a minus symbol to the sorry, not symbol. It's a minus sign to the training sample. If we give it a minus sign, the weight of this particular training sample will reduce in the next round, and it is less likely to be represented by the random subset. Okay. Now, if we use 0.5 minus is correct, what we will have if we have this calculation? Nope. That is, we have the samples that has been wrongly predicted have some value of positive 0.5 corresponding to them, and the symbols that has been correctly predicted have minus 0.5 corresponding to them. If we multiply this with 0.2, that way we have the desired minus or plus sign for each of the sample. Okay, that's the sign. Let's quantitate sample sign. And now the weight update becomes straightforward. Let d equals d times not bigger than exponential simple science 1 times alpha 1. And let's have a look what d we will have. Oops, I forgot not it. Right? Look, in the next round, we will have more chance to sample the first 3 training samples which has been wrongly predicted in the first round, and we will have less chance to sample the remaining samples. But there is one problem issue left, is that this d has been updated, and now the summation of the d will not be 1. Carefully, do not run this cell twice or more than once, because look, when we update the d will get multiplied by these factors. If we run the cell twice, it will be multiplied multiple times, and I think in that case you need to go back up to the first initialization and run all the cells again to get the numbers correct. Now let's have a look at the summation of the weights in d. Look, that is not 1. How to normalize d to be 1? That is simple. This division equal symbol means let d equals d divided by something, and on the right hand side, let d be divided by the summation of d. Note that if you do not have much experience in programming, the right hand side of an equation will get executed or evaluated first before any value of the left hand side will be updated. So there is no contradictory here. We first use the old value of d, not quite old as the original one, but the updated value that has been out of normalization. Use this value of d, take the summation, and this summation will give us that 0.91 something, and use this summation to normalize the values in d. And after this step, we would expect d have exactly summation of 1. Let's run this step. This cell could be run multiple times. Why? Think about it. Yes. So now we have a new set of d. What we need to do? We need to proceed into the next stage, which is to regenerate random samples from the data set. Let us have this part. Look, if you notice that now in this subset, the first symbols are better represented. Also, maybe out of bad luck, we still do not have an ideal good representation as what we have seen in the previous slide, the example on the slides. So all the wrongly predicted values have been represented, concentratedly represented in this stage, and we ideally have the second stage predictor reflect and correct the error from the first stage perfectly. But the point of the procedure is go like this. And I will stop here for this manual construction of the boost algorithm. and let us see what we can do in class. And of course, you can proceed with manual steps to get a better understanding of this algorithm. In the following, we will build an automatically constructing scheme of the Adaboost algorithm. The Adaboost algorithm. To have examples to show how the algorithm works, I want to first make a simple data set to have a more intuitive demonstration. Okay, I would not go to the details of each step of construction of the dataset, just to give a few comments. The dataset has made two sets of samples. The first set of sample is a two-dimensional normal distribution. To generate normal distribution, we used this RANDN, N for normal. And there are these 200 samples in this first subset of sample, and this dimension 2. So that is the 202-dimensional normal distribution distributed with distributed at the origin of the two-dimensional plane, and by multiplying the 0.15, I would have the standard derivation of the samples approximately, not approximately, standard derivation is 0.15, and so I would assume these samples will concentrate in a circle which is about 0.45, because look, almost all samples of a normal distribution would end maybe 3 standard derivations. We will show the samples later if you cannot understand at this point, don't worry. And the second subset of the sample is distributed on a ring. Look, to generate these samples, I have two parts. One is the angle, and the angle is distributed uniformly from 0 to 2 pi, and also with a radius, and the radius is from 0.4, which is the minimum, to 0.2, because look, this is the uniform distribution between 0 to 1, and this has been multiplied by 0.2. So this part will generate samples from 0 to 0.2, and when we plus 0.4 onto this 0 to 0.2 samples, we will have a random variable uniformly distributed from 0.4 to 0.6. And if we use that as the radius, look, when we generate it, we use cosine of the angle, sine of the angle multiplied by the radius. So basically we are generating a ring. So this is the data, and we'd like to give some we give a label of 0 to the first part of the samples, which is the inner circle, and 1 to the outer ring of the samples. We can scatter those samples. So the first part of the first argument of scatter is the samples x coordinate, and the second part of second argument is the y coordinate. And let us color those samples according to their y values, give it some larger size, and use a more clear color map. I particularly like the summer color map. Check. Well, this is our sample. Okay. And to have Adaboost, we need first some weak classifiers. The weak classifier we would like to use in this example is pretty weak. What we will use? I call it flat cut. So our classifier can only do two things. One is to draw a horizontal line along, oh no, not this way. Draw a horizontal line along the in the two-dimensional plane and cut the plane into the upper and the lower part. And on the other hand, it can also cut the plane this way from the left to the right. So it will give one value to all the samples for in the left hand side or the right hand side, or all the samples upper or lower. So that's all. That's all we can do use the weak classifiers. Obviously, we cannot use only one weak classifier to classify those samples, such a distribution of the data satisfactorily. The best we can do, I think, for a single classifier, perhaps, is to cut something here or cut something here. But let's see what an Adaboost algorithm can produce for us. The first step, of course, let us build a family of weak classifiers. We call it flat cut. Initialize itself. When you define an object template that is a class in Python, generally you put all possible potentially used attributes in this function. So what we'll do is we call it the self cut mode to be. You do not need to give it any meaningful values at this stage, but a good convention is to have all the attributes allocated somewhere here. Determined and self.threshold. Threshold is where we do the cut. Okay, that to be known. And in following the convention, we have now be familiarized with of scikit-learn. We want to provide a predict function for this object. The function in the object template that is class, mostly they will have the first parameter named self. And the name of the parameter is not mandatory according to the Python language, but it is a very good suggestion to just follow the convention, call this parameter self, because this parameter always refer to the object that is initialized from this template. Okay. This self, and following also the naming convention, we call the input, call them data. Let us see if self mode horizontal greater than. Well, I think I have misnamed a little bit. Well, consider a convention. Let's say this. If we call the cutting mode to be horizontal, the weak classifier will be concerned on the first dimension, that is the x coordinate of the input data. So this way, we mean the cutting point is on the horizontal axis, but the cutting line will be a vertical line, but we do not consider the cutting line because the definition of the weak classifier is the cutting point. And if the cutting point is on the horizontal axis, we call it horizontal cutting. And the GT refers to greater than. That means if in this cutting mode, when the first coordinate, first value of the data is greater than that threshold, we will classify that data to be of label 1. Otherwise, it will be label 0. Okay. To implement this such a classification scheme is easy. Just we can just return data, the first coordinate okay. Let's check. Okay, but I do not like to do this well conversion every time. So let us call it pred equals this. Okay, and return pred type numpy float. So if you allow me, I will quickly program the remaining part of this simple weak classifier scheme. Okay. Finish the prediction scheme of the weak classifier. Look, it has 4 ways to cut the plane. The cutting point is on the horizontal axis. The cutting point is on the vertical axis. When it's greater than the threshold, we classify it as 1, or it is less than the threshold, we classify the samples as 1. So that's it. And the second function is of course called fit. Self data target targets. Okay. To fit such a weak classifier, we use brute force, so we do not worry about the optimization scheme very much. To use the brute force, we will iterate over all possible cuttings. So to do this, we will try the 4 ways of cutting: the horizontal greater than, horizontal less than, vertical greater than and less than. And for each of the cutting mode, we will evaluate from the smallest possible cutting threshold to the maximum possible, which we achieve like this. We first extract the x and x, the min and max value along the x-axis of the data. This is the x horizontal value of the data, have its minimum value, and also let's have it maximum value. This in this way we get the range of the on the horizontal direction of the data, and similarly we get the range of the data along the vertical axis. Okay, then now let us allocate a couple of variables. That's the best threshold and the best mode. Both are unknown now, but now we allocate a bet accuracy, which we initialized as 0. That means whatever width. If we cut the data, we should have something better than this one. And the training process is actually consists of loop over all possible cuttings. Please allow me to copy this part of the code here. Loop over all the cutting possibilities. The first is to use two different ways of cutting at the horizontal axis, and the threshold will be iterated from the minimum x to the maximum x. And this linear space means NAPI will give us an equidistant series of points from the minimum value to the maximum value. And using these values as threshold, we would look, because we now directly give those cutting mode and cutting threshold to the attribute of this object. So we are able to use the prediction function of this object to do the prediction, and compare the predictions to our training targets. That we get the accuracy. And if the accuracy has beat the historical best of this particular weak classifier, of course, we would update the historical best and take a record of the best cutting mode and the best threshold. And we do the same thing along the vertical axis. And after we have done all the iterations, let us give the saved best threshold and best cutting mode to our classifier. This is for debug purposes, just to print out the values. Let me put a pair of parentheses for Python 3 users. Okay, that is our weak classifier. Have it defined, and let us have a check. Weak classifier to be flat cart. Well, that is to get an object as our familiar way. We let it to fit to x and y. Okay, see how it goes. Well, look, it has a horizontal card, and the threshold is this way. See how it casts data. Let's cost dot predict x scatter x and x 1. Let the color to be p. See map summer. Good. That is as much as a single weak classifier can get. Okay. Sure. Before we start building the Adaboost algorithm, we need another piece of preparation, which is just to build an ensemble classifier first. So now when we perform the Adaboost during the process, we can evaluate the ensemble online, on the fly. Ensemble predictor. So let me copy my code here, and let us have a brief instruction that ensemble prediction accept S and of course a set of classifiers. The set of classifiers is just our weak classifier. But look, the ensemble does not care what kind of classifier we actually use for the weak classification. As long as each of the ensemble classifier has a P, that is a predictor of the classifier itself, and an A, that is the alpha value. So the classifier itself must provide a function called predict, which accepts the data provided to the ensemble predictor, and return the prediction. And the prediction is, of course, should have one of the target values, either be 0 or 1. Conventionally, I think in Adaboost, if you read Adaboost literature, many of the classifiers will use the prediction to be minus or plus 1, but that are, well, technical trivialities. So we just use 0 and 1 to be consistent with our weak classifier. So in each of the iteration, we will evaluate one classifier on the dataset, and when the classifier classified a sample to be 0, we give the accumulated 0 classification the weight of this classifier. Otherwise, we give the weight of this classifier to the accumulated prediction of the label 1. After all classifiers have what they have to say, we consider if the label 1 has, for all those samples where label 1's weight is greater than label 0's weight, we will return the prediction of 1. Otherwise, we will return prediction of 0. That is what an ensemble classifier predictor does. Okay, let's define that predictor and start building our Adaboost. So we first allocate a random generator, so to have our algorithm has a repeatable behavior and have some initialization. I will copy my initialization here. Let's see. This n is just for easy typing. That is the number of training samples. And the subsample size here, as I have said, it may be or may not be equal to the training sample size, but in this example, I will let it to be the same as the training sample size. And that capital T represents the maximum weak classifier we will build into the Adaboost classifier. And in this simple construction, I will not give other stop conditions. So this will be the exact number of weak classifiers we will have in our ensemble. And that D is, as we have introduced above, the initial weight of each sample. That is 1 over the sample number. Look, because we already have the sample number, let's just put an n here. This is the index of our first subsamples. So as we said, we do not necessarily need to sort this index. So we save the sort function here. And let's extract the stochastic subsamples for the first round of training. And now our ensemble has been initialized as empty. The loop is for each t in range capital T. So let us create a weak predictor for this t, flat cut, and let us feed our weak predictor to the subset we have just sampled, and let us have a look at the predictions. Oh well, we haven't actually created this object, so we do not have the automatic completion works for us for now. Let us just type out. So this prediction has been done on the training samples, and the next step is, of course, let us calculate the weighted error. Let's put a W here to show it has been weighted. Okay, that is prediction not equal to the target value y. Okay, as type numpy float element wisely times the current sample width, and the epsilon of this round would be this the summation of this error. Note that now we need I'd like to put some safeguard, because for example if for good or bad reasons we happen to have some weak classifiers that can perfectly classify this subset of samples. Note, although a weak classifier is not able to classify the original training sample, but because we are randomly sampling a subsample of the training samples, it is possible for some singular subset of the training set, so that even a weak classifier might be able to perfectly classify the subset of samples. If that happens, the error will be 0, whatever the weight of the samples. Then, when we try to evaluate the function which has the this epsilon as the denominator, we will arrive at an error. So to eliminate this peculiarity, let us do a manipulation. That is, when there is an error, use the error. When there is no error, have a very small value, substitute the error in the evaluation of the equation. And then we will be able to calculate the alpha. Let us just copy the equation. Minus PS, or EPS perhaps is not a good variable name, because a lot of programming language use EPS to represent very small value in that language. Let us call it EPS of this t. Okay. And the next step is to update our sample weights. Let's call it d. It's multiplied by element wisely, or multiplied by the exponential of well, we have already multiply this error with weighted this error with d, so we cannot reuse the prediction, which could be wasteful. Let's do this. Errors equals this one, and errors weighted to be errors times the errors weighted. Okay, let's check. Use this one. So now we have these errors. This array will have an element of 1 if the classifier make an error at Ensemble or 0 otherwise. So following the scheme we have used previously, but previously remember we use is correct array, but now we have the error array. So we can do this error minus 0.5. In this way, when it's wrongly corrected, predicted, we will have 0.5 value for that sample, and so we need to multiply the 0.5 by 2 to have 1 plus 1 for wrongly predicted samples. Use that to multiply by the alpha. So now we have our D, and let us normalize our D. Sure. Okay, this way we have finalized all the steps we have in one step of the Adaboost construction, and of course we need to see what we have achieved. Let our ensemble to be appended with a pair of elements. One is this week. Oh no, not this week. Week prediction. Okay, and the alpha. Let me save this, and allow me to copy some visualization code so we can check how the algorithm performs. I'd like to draw 3 plots. In the first plot, I will draw the random subsamples and the prediction of the weak classifier on the random subsamples. And in the second plot, I will draw the entire dataset and show the ensemble prediction on the dataset. And in the third plot, I will draw also the entire dataset and show the current width of the dataset for the next round of subsampling. Of course, we need a subsampling. To do this, we just copy what we have used above and paste it here. Have a check, choice, and this. Look, this needs to be n. As discussed above, this n can be different from this subsample size. Although we have them equal to each other now, but remember that this please do not mistake the rule of this argument with this one. This means to sample from all the original data set, and this one is what the result subset size is. It can be the same as the original data set, but this one is mandatory. It must be the size of the original data set. Okay, so hopefully this will work. Well, silly error this week. Look at the error. it shows on line 30 there is an unnamed variable. Where is line 30? If you click escape ESC on your keyboard and let us use the up and down key, arrow key, to move the cursor to a cell, and now when we click L, it will show you the line numbers. Let's find the 30th. Okay, it is here. Let's run it again. Well, looks it is working. So the first Wee classifier is like this way, and now, not surprisingly, the ensemble works exactly as the first and the only classifier. When you have the second classifier, well, it seems it dominates the ensemble. But when you go on, the ensemble starts, well, building interesting predictions. If we go this way all the way along, so at about maybe 20 or something like that, well, about 20 Wee classifiers, we pretty much use this very simple flat cut Wee classifier to reproduce an interesting distribution on the data plane.